Hey everyone, Jerry here from LlamaIndex. Welcome back to another episode of the LlamaIndex webinar series. And today, the main focus of this webinar is on advanced tabular data understanding with LLMs. And to that end, we're excited to feature two leading research works in this area. One called Chain a Table, featuring Ziyong Wang. And then the second, the paper is Rethinking Tabular Data Understanding with Large Language Models, featuring Tianyang Liu. And so Chain of Table is a cool paper that basically combines chain of thought with tabular reasoning in a novel way to try to, answer advanced tabular questions over your data. And then the second paper, Rethinking Tabular Data Understanding, does a deep dive analysis of how good LLMs are at symbolic reasoning, textual reasoning, and also proposes some novel techniques to try to improve the performance. And so we'll do 15 minutes for each presentation and then do around like 20 minutes of Q&A at the end. But the first presentation will be Chain a Table by Ziyong Wang. And so without further ado, feel free to take it away.
Sure. Thanks for the brief introduction, and thanks for everyone being here for this presentation. Today, we're not going to talk about the recent paper, Chain of Table. As Jerry just mentioned, it's about the chain of thought and the tabular understandings. So let's see how we combine these two things together. Oh, I forgot to mention that this paper is a collaboration between the UC San Diego and the Google Cloud AI Research. And I have to thank all my wonderful collaborators. This work cannot be done without the help from them. By the way, the paper link is at the bottom, so feel free to check it online. Okay, so as we all know how large models are so powerful these days, it can answer millions of questions just with one click. However, when it comes to the tabular data, things are more complicated because tabular data are not just text. So a very straightforward way to let large model understand tabular data is to incorporate the tables into Markdown format or other textual formats in the prompt, as shown in the screen. We have a table, we have the question, we convert the table into a Markdown with pipes in the middle. Then this is kind of a new prompt, a more complex prompt. And the large model are trained to understand the Markdown format, and then they can do the tabular reasoning. However, we don't think this, we all agree that this simple prompt is not perfect. In the academia, there's a lot of different ways to improve the textual reasoning. For example, the few shot question answering or the chain of thought question answering. But if you compare all of these methods, you will see in all these methods, tables stay unchanged and are merely used as context during reasoning, which means all we did here is just add a table in the context. Tables are in a Markdown or whatever format you like. It's just like other long passages in the prompt. That's it. However, things are not that easy. We want to better leverage the tables in the reasoning when we're doing tabular reasoning. So we just consider how our human process and understand the table. Basically, what we are doing is that we may think step by step and update the table iteratively to better understand the tabular information. Here is a brief case study of our chain of table. You can see on the left, that's the original table, which is large, which is complicated, which is just involve a lot of different information here. To answer this question directly is not that easy. So just like how we human understand this table, we ask large model to do iterations of updating, of the selecting of these operations on the table. Later on, we will get a much simpler table. And at this step, large model is not that hard to get the correct answer. So this is a simple demonstration of the tabular reasoning process of chain of table. From left to right, there are 4 iterations for this example. We use these different operations on the table, like the select column, group by the column, group by the rows, and sort by a certain header, something like that. Yeah, this is figure 1 of our paper. which is the overview of our method. We compare our method with two different type of method. One is generic reasoning. It's like the very general text reasoning techniques like chain of thought, list to most, whatever, or the textual reasoning method. Then the other type of reasoning is called program-aided reasoning, where the method incorporates some programs like SQL because it's a tabular reasoning. So in this demonstration, we can see generic reasoning and the program-aided reasoning are not that good at tabular reasoning, which gives some incorrect answers in this case, while our method can leverage these iterative operations to update the table and come to the final correct answer. Yeah, to be more specific, in the red frame here, we let large models to think step by step, updating a given table iteratively to reflect each part of a solve process. This process is similar to how we humans solve the table-based questions. You can see we look from step 1, sample the operation, step 2, generate the argument for the operation, and step 3, transform the table to store the tabular reasoning process with the operation and the arguments. After a few iterations, chain of table makes tables to be simpler and more manageable segments. Then the large model is able to answer and analyze each part of the table in depth. You can see how simple the final table looks like. Only 3 rows and 2 columns, that's it. Let's just dive a little bit into the details of this method. In the step 1, I just mentioned, we will sample the next operation from the operation pool. And here, when we design our prompt, we include 3 important elements here. The first is the latest intermediate table. The latest means that this table is just transformed by the previous operation. So as you can see from this case, this table has already been processed by the add column and the select row, these 2 operations. So the table here is the intermediate table. It's not the origin table. It's already simplified and aggregated. Yeah, this is the first part, the latest intermediate table. For the second part, for the question, as always, we need to let Llama know what we are doing here. What is our major task? That's a question here. The third part is the operation history. Operation history is in the middle of this figure, which are the add column and select row. We need to let our model know what operations are already there in this entire pipeline. So the large language model will know, okay, we need to do this task, which is a question. How many steps are we already done for this question? That's the operation history. And what is our next step towards this latest intermediate table? With all these 3 elements considered, we will prompt our model to select an operation from the operation pool. In this work, we have all these 5 operations here. And since the framework is quite intuitive, we can enlarge this operation pool with any operations you like for your specific tasks. And we find these 5 operations are commonly used in tabular reasoning and are good enough in our experiment. So we didn't include too many different operations here. And in this case, we select the next operation, group by as our next operation. So the next step is to get the argument for this operation, for this group by operation. Similarly, we consider a few different elements to prompt our model to get the argument. The intermediate table, the selected operation, and the question. That's quite simple. And here I want to emphasize is that different operations may have different arguments. That's quite intuitive, right? If you want to add a column, you need to know the new column header and new column content. But if you want to group by the rows by a column, you just need to know the header of the column. So consider all of this. Since the operation is already decided, we just like a lookup table. When the group by decided, we just find the corresponding arguments for it and prompt our model with all these informations and get the answer. In this case, the group by columns argument is country, the column country. Then we can wrap this operation and this argument together and get our and process table, get the new intermediate table at the next step. Yeah, so much for the methodology part. Let's dive into the experiment. In our experiment, we have we have two data sets here. One is table-based question answering, wiki table question. That's a very common used data set in the literature. This question answering data set looks like this. We have a table, we have a question, and the expected answer is given here. One tricky thing about this data set is that all these questions are very complicated. Some of the questions are very complicated, and it is not that easy to solve it by the SQL, because sometimes SQL is not that well enough in solving questions. The second data set is table-based fact verification. You can consider this as a true or false question. Given a table, given a statement, all you need to do is to tell whether the statement is correct or not based on the context. These are our baselines works in this method. And into a few shots QA and chain of thought QA, all these three methods are quite familiar to everyone. So I just skip the introduction of them. For the program-aided reasoning, which could be not that popular. So the first one is text-to-SQL, is to convert the question into a SQL query. So SQL is also a part of program, so we put it in the program-aided reasoning. There are a few advanced works on tabular reasoning in the past. One is called Binder. I put the link here. You can look it up online. And for the Binder work, it is to enhance the large text-to-SQL by incorporating large models as APIs, because the pure SQL is not that powerful enough. Sometimes it may encounter something SQL cannot reason about. So this work just incorporate large model as API to solve some conditions or some statements the pure SQL cannot solve. In the data is also another advanced tabular reasoning work. It involves two parts. One is to decompose the question into a few supportive questions. It's similar to the chain of thought. The second step is to decompose the table into a smaller table to solve the token limitation issues. Yeah. So comparing with all these baselines, our work chain of table achieved the best performance. You can see here we select 3 different large models as our backbone. The PaLM2 from Google, the GPT-3 Input 5 from OpenAI, and the Llama 2 from Meta, which is an open source large model. We can see chain of tables surpass all baseline methods on 2 data sets across both the closed source large models and the open source large models. So basically, we can see chain of table is a very competitive and a competitive method to do the tabular reasoning. We attribute this good feature to the intermediate tables and the chain of operations in the reasoning process. Another findings from our work is that we find this chain of table reasoning is more robust on the harder questions. As I just introduced, we have a long chain of operations, and we assume the longer chain means the harder questions. So as you can see from this chart, the right part is longer chain, the left part the shorter chain. So we believe the longer chains means harder questions, so the harder questions will be on the right. So we can see all these baseline performance drops when answering the harder questions. That's quite intuitive because they are harder. Performance should be lower. Well, if you dive into it in more detail, you will see, compare with these two baseline works, chain of table shows the minimal decrease. The chain of table is the blue bar. The decrease is not that remarkable comparing with the data and chain of thought. So when we have harder questions, the chain of table can still provide you a good answer. The other finding is that the chain of table is more robust on the large tables because large tables also means quite harder here. So we divide the tables into 3 categories: small, medium, and large, based on the token numbers. So the performance, the overall tendency is similar. The performance drops for the tables of the larger size, but the chain of table is still more robust to them. Yeah, that's all for the introduction. And the main takeaway here is that chain of table enables the step-by-step reasoning with table inputs by simplifying complex tables into more informative and manageable segments. This breakdown into the digestible segments leads to a more accurate understanding of tabular data. So thanks for the listening, and I guess the QA will be after Tianyang's presentation, so we can wait a bit, and then we can do the QA. And that's all. Thank you.
Great. Yeah. So there's a ton of questions already. And actually, I think if you don't mind, I'll just kind of quickly shoot off 2 questions more specific to the train and table paper. Some of these are more general questions that can wait until Q&A. The first question is, what's the limit on the size of the table to like, does it have to fit within the prompt? And how do you think about that?
Yeah, because the tabular reasoning actually introduce more context into the prompt, which is the table, right? So we need to represent the table in the prompt, and then that will like make your prompt longer. So the token limit is always a problem. Even if larger models can include long prompts, if you have too long prompt, then the performance will also drops. So basically here, let me go to one slide here. Yeah. Basically, in our overall operations, after a few iterations, the size of the intermediate table will be much smaller. So I believe this is a very promising direction to kind of make things easier because they're always very large tables. We cannot solve it with large models, but we can introduce a few operations here during prompting, because during prompting you can just select the first few rows or first few columns, something like that, to make the table smaller to fit in with your prompt and to improve the reasoning ability of the prompt.
Cool. And then the next question is just, does this technique work with multiple tables, and or how would you kind of like adapt the technique to get this to work?
Oh, I see. Yeah. Actually, in this work, we didn't touch the multi-table scenario. As you can see, all these 2 data sets in our work are just single table scenario. But I believe because this work is not like a very integral system, it's more like an idea. So you can introduce some some more tabular operations, I believe like if you have multiple tables, the operations you need is like maybe table join or something like that. You can introduce those operations here and prompt our model to do the table join and to merge multiple tables together or conduct reasoning over different tables. Yeah.
Okay, I keep seeing questions flow through the chat, and I do want to be respectful of Tanion's time as well to give him enough time to present. But maybe just one more question, just before we end this section is, are there some types of tables where like this technique always fails, or does this generally kind of generalize well to like a certain class of tables? What challenges and just like use cases have you noticed where like, this thing does well, this thing does poorly?
I think the failure cases fall into like two categories. The first one is mentioned a lot, just like the previous question. That's about the table size. Let me show you here because as you can see from the operation pool, there are a very hard operation called add column. For this add column, we need to prompt our model to get the content of a brand new column. So assuming we have very, very long table, there are a lot of rows, then the quality of this operation will be highly influenced. So the table size is always a problem, even if we have some advanced ways to make the alarm with the table smaller. That's the one thing. The other one is about the question size. Some of the questions is really, really tricky, and it's not like a tabular reasoning. For example, I can give you an example like for this wiki table question table, you can see the upper part is assuming our question is not like how many events, how many like where this event happened, something like this. This is like a reasoning. Some questions like what is in the first row of this table? What is in the second row of this table? Then this question is not like a reasoning task. It's like just check the table, then you will see the answer. And in these cases, as we all know, our model is not good at counting. So that could be another problem for tabular reasoning works with large model.
Got it. Yeah. Great. Well, thanks, Zillan, for your time. And we'll kind of defer some of the questions towards the end. But in the meantime, Daniel, feel free to take it away.
Okay. So let me first share my screen. With maybe some bug here. I'm trying to fix it.
If all else fails, feel free to send me the slides. I can share for you. But yeah, just let me know.
Yeah, so there's something wrong with my computer. I just cannot click the share my screen thing.
Sometimes if you leave and rejoin it could work.
Okay.
Great. Yeah, I think this works.
Yeah, okay. Let me go back to the first page. Okay, so hello everyone. So my name is Tian Liu. I'm currently a master student at UC San Diego. So I'd like first to thank Jerry for inviting me. And so good morning, good afternoon, or good evening. So wherever you are in the world. So I'm so happy to have the opportunity to present this paper, so which was completed under the under the guidance and collaboration of Fei Wang from USC and also Professor Mo Chen from UC Davis. So this paper is called Rethinking Tabular Data Understanding of Large Language Models. So so first let me introduce some motivation of the motivation. So the initial motivation behind this paper is actually quite straightforward. So over the past few years, so we have witnessed the rapid development of large language models, some advances in the AI alignment technologies such as instructor tuning and also human feedback reinforced learning. So from the early days of simple left to right auto completion tasks to now so engaging in basic conversational interactions and now to the models capable of following complex instructions given by users. So in an effort to enhance the accuracy of the model responses. So I believe current models are intentionally designed to mimic a chain of thought reasoning process. Therefore the paper kind of aims to explore how large language model try to comprehend tables in zero shot settings. So meaning that without any demonstration or examples and to explore whether large language models can accurately perform reasoning tasks over tabular data. So additionally, we actually know that large language models inherently struggle with handling tabular data due to the necessity of linearizing the inputs. So the image on the left presents the tables as we see them. So where we can actually clearly locate and understand the information in the table. So no matter horizontally or vertically. However, for the input to a language model, the data from table must be spread out into a sequence as shown in the right image. So the linearization process may use some special tokens new line characters for separation. Which inevitably leads to information loss like the structure information of the table. So in this paper, so unlike developing a framework or methods like the chain of table, so ours can be considered more of an analysis paper. So but we do come across to find a simple method that can improve accuracy, though it might not be that efficient. So as mentioned earlier, so our goal was to explore the capabilities of large language models under zero-shot learning setting. To this end, we actually categorize our approach into two types. The first type is the first type is like the textual reasoning, or maybe we can call it generic reasoning. Which involves direct reasoning over the table to answer questions, and another method is symbolic reasoning. Which is widely used today. So symbolic reasoning generally involves interacting with some external tools or functions to directly get an answer or progressively reasoning towards a final answer in a react like style. So specifically, there are various techniques within the two categories. So for example, for the textual reasoning, one might generate an answer directly without any reasoning, or to prompt the model to engage in COT reasoning by adding instruction like think step by step. And also more complex instruction could also be used to achieve more detailed and or like a refined reasoning, and symbolic reasoning could involve converting text to SQL queries to generate an executable program, or like interacting with the path environment to incrementally approach the final answer, and also more complex frameworks could also be employed for better outcomes. So our experiments primarily use the two basic approaches as highlighted. So we just call them like the direct prompting and also Python agent in the paper. So the paper focused on approaches like focus on topics from the following perspectives. So first, we try to investigate how large language models perceive tabular data. Like we are trying to understand the model's understanding of table structures, and then we dive into the performance comparison between textual reasoning and symbolic reasoning for tabular data reasoning, and finally we're trying to explore how to integrate the two reasoning methods to enhance the overall performance. So first, I'd like to talk about one thing is about the table transposition thing. So actually, the table transposition can help us and can help us understand how the large language models understand the table. So actually, so for humans, so whether a table is transposed or not, that does not significantly impact our ability to understand it, because transposition merely only change the structure instead of the content. So people can change the preservation from horizontally to vertically. So however, for large language models, transposition can have a significant effect. So this issue was actually uh was actually discussed by my co-author in the paper two years ago, but by that time they only focus on open source models, and that had been fine-tuned. So in the context of today's large language models today, so we aim to see if the large language model could understand table structure that had been transposed, like understanding the table structure. For example, look at the example here. So we found that the models actually can semantically extract the table's headings quite well, but they kind of like struggle to correctly answer the simple question of like whether these tables were in the first row or in the first column. And so if we check more examples on the chat arena, so we can actually say all of those models said that the headings are located in the first row instead of the first column, because so we can see that we can see the table. So actually the headings are the headings are located in the first row, so are located in the first column. So we actually call it a row table, but all the models here feel to identify the headings location of the table. So the most important thing about those table with headings located in the first column is that, so if you are trying to interact with Python shells, so what we call the symbolic reasoning, the large language model can semantically understand the table. So which means that they will simply consider them as column headers, but actually they are not column header. So the large language model will try to write codes to retrieve the columns, but it turns out to be errors. So we can see the result here. So if we add a perturbation of transposition and and if we are using symbolic reasoning, the performance drop by nearly 80%. So actually the paper explores several straightforward methods to mitigate the effects of such perturbation, or like to handle this table variance. Without compromising the handling of common table. So this method is questionable. So if you are interested, you can actually refer to the paper. So another thing about table structure thing is that the problem of column localization. So which is actually quite crucial for understanding the structure of tables. So as mentioned earlier, the need for the need for the linearization process can actually complicate the process. Can actually complicate the process of locating items within the same column. So however, as we as we stated before, tables can be semantically understood by the large language models, so making the column localization less challenging in certain contexts. So for example, in the for example, in this case of the transformer based base models, so when computing the attention scores, so it's actually unlikely a value like 6 feet 1 would be correlated with a column like weight. Let's actually suggest that thematically column localization can still be relatively straightforward for less models. So now let's look at another example. So how column localization can largely affect the results. So we can look at the table, and so the question is about who has the top second score. So actually we can actually as a human, we can very easily to identify that the top second score is 132, and so we can answer the name is Andres. And now we can see how large language model do the reasoning here. So actually, first large language model say that we need to find the highest value in the second column of the table. So that's a very good start. But then it successfully analyze the table, and then extracted the highest value in 132. But finally, so when they try to find the name, so large language models trying to reason that the 132 was achieved by both Andrews and Matty. So we can actually say there's another 132 here. So finally the large language model gave the final answer is the final answer is 2 people, but actually the second 132 is not it's not it's not related to the second score. This observation is this observation kind of like kind of like review, like, so when several columns, so for example, especially some agent ones contain similar data. So the large language models may find it difficult to accurately locate specific specific information while reasoning directly from the table. So this difficulty arises because thematically the data across across these columns are quite similar. So making it hard for the model to distinguish to distinguish them between to distinguish between them during the textual reasoning process. Okay, so then let's talk about the comparison between symbolic reasoning and textual reasoning. So actually so in our paper we actually found like the symbolic reasoning actually does not necessarily perform better than textual reasoning. This is actually because for the model like G like GPT 3.5, so symbolic reasoning indeed good at some like some counting tasks, but sometimes sometimes the coding part is it just not that as stable as what we want, and also the symbolic reasoning might kind of like like some semantic depth during the reasoning process, but actually the textual reasoning can sometimes provide more robust more robust reasoning over the table semantic information. And then so we kind of like proposed a kind of so this result is actually kind of like unexpected during our experiment. So we actually kind of like trying to simply aggregate the different reasoning paths from like from symbolic reasoning and textual reasoning, and then we get the total performance. So here so here I can explain a little bit so why the simple aggregation works. So the effectiveness of simply aggregating the different reasoning paths can be understood in the context of of the ideas in the like tree of thought reasoning, and share some ideas with the offline reinforced learning. So where the self consistency can be seen as an indicator of the model's confidence in the generated output. So this confidence score can also reflect the model's proficiency degree, or how well suited it is to solving a particular problem. So if a model is good at so if a method is good at a specific area, such as symbolic reasoning in the context of counting rows, so it is less likely to produce incorrect answers. However, large language model typically struggle with a task like counting or like calculation. So when we employing like textual reasoning, the model tend to generate less confident and more various and more various answers. So so the self consistency can work if we just trying to to do a majority voting on like five symbolic reasoning paths, and then five textual reasoning paths. Yeah, so so that's all my presentation today for the paper, and the paper is just about an analysis of how the large language models how the large language models today perceive tabular structures, and also how the two mainstream zero-shot methods can how they perform under the tabular data reasoning tasks.
Great. Well, thanks, Taeyang, for the presentation. Yeah, it's a cool paper on the analysis of how robust LLMs are to different types of techniques to understand tabular data, as well as a simple like the mixed self-consistency technique we implemented as a LlamaPack. We basically just fire off like a bunch of different queries at once, try out a bunch of things, and then aggregate the results at the end. And so for those in the audience, we have LlamaPacks for actually both papers, both the chain of table paper as well as the mixed self-consistency technique that Taeyang proposed. And so if you want to try it out, feel free to, and of course, like adapt, modify it to your own needs as well. Just tracking the time, I know there's a few questions in the chat. I do want to go through some general questions for both of you. And the first question I want to ask is basically, as LLMs get better, right? As LLMs advance, assuming GPT-5 comes out, Gemini Ultra 2, Mistral, like whatever, some version. As these models get better, how do you see the techniques and the need for kind of more handcrafted techniques for tabular data evolving over time? And how do you think these approaches will change to kind of adapt to better LLMs? Maybe we can start with Ziel. Sorry, Tang, go ahead.
Zilong yeah, he can go first.
No worries. If you already prepared answer, you can go first. No worries. Yeah.
Yeah, Tang, how about you go first? Yeah.
Okay. So actually for me, so I actually feel like so for example, in the future, I guess maybe how to say so like I have said in my presentation, so I believe there are some problems that are the inherent problems under the transformer structure. So in the future, I believe so if we want to really uh do do a perfect performance on the tabular data. So we must trying to combine the symbolic reasoning part. So especially we will have to have to make the model trying to interact with a certain with with certain environment coding, so that they can get the final final results from the symbolic part instead of the pure reasoning part, because the large language model cannot do counting thing. So I believe so in the future. So if the models evolve in the, I believe especially in the coding part, the tabular data reasoning will definitely benefit from that part. And then so we can trying to make the table connect to the connect to some coding inference platform, and then get the final answer. Yeah, so that's what I think about.
Got it. And Ziel.
Yeah, for me, I'm thinking that although we have already seen the remarkable performance of our models, but I guess everyone should agree that the large model's performance is not perfect. We all suffer from the hallucinations, and when it comes to the industry, the real product, all these hallucinations are not tolerant. I guess in the future, the humans still need to do some work, right? We cannot depend entirely on the large models or whatever models in the future. So I guess I believe the large models or any models should be like some assistant. It will boost your efficiency. Maybe for a boss, maybe you can hire fewer people. That's a happy ending. But for employees, I guess these tools can make your life easier. You don't need to do some boring works, but that also means some simpler works are not that necessary. Yeah, just like some basic work can be substituted by the large models or maybe other powerful models. Yeah. In short, just like the model should be an assistant, not the ultimate employee. Yeah.
Yeah, interesting takes. And then the last question I was gonna ask is there's like 5 questions in the chat around table extraction from documents, which I know is a little bit orthogonal to your work, which is more on just given a table, try to understand it. But I'm curious if you have initial thoughts on the challenges as well as techniques around table extraction. Maybe we could start with you, Zion.
Yeah. Actually, I did some work on the visually rich document understanding in the past, which is to understand the document images. I guess this is quite related to this question because in real world tables are not just in digital form. Maybe they are in documents. So as I replied in a few questions in the chat, so the most straightforward way is to recognize the table from the document from the images, and then we have a digital table. We can use whatever techniques here present here. But the table recognition is just like another topic. But the performance is not perfect. It's like OCR, although we can improve the performance, but it's not always the perfect. So another way is to use some multimodality large models, and it can take the table as input. So just directly recognize it as an image. But the thing here is that a lot of concurrent works just treat the document images in a similar way as photos. But you will see it's quite different, right? For a photo, you can see a horse on the ground, a table in the room. But for document images, what you care is the detailed characters on the page. And these characters are so detailed, you cannot change it a little bit. If you change it a little bit, then it's a different character. The meaning is different. So I believe in the future, the multimodality large model should be a more promising or more useful direction. Well, some techniques need to introduce to make it different from the ordinary photos. Yeah.
Makes sense. And Tianyang, any takes there?
Yeah, so actually, when I was making the slides, I actually used the the GPT-4 version to convert the image of the table to a markdown version, so that I can copy paste. So actually I guess I guess if we want to really extract the table from a PDF document, so definitely we will need some more powerful models, and also we can actually have some techniques since if the model is if the table is really large, so we can actually trying to narrow down on unlike specific part, and then we can trying to finally trying to aggregate the whole table. So yeah, I guess yeah, so I kind of agree with Zilong about the importance of the vision models.
Cool. Thanks for the answers, and yeah, thanks for taking the time to present both of your works. Both are awesome techniques, train a table and a lot of the analysis and like the tabular understanding paper and the mixed self-consistency technique. So thanks for taking the time to present, as well as answering all the questions. And to the audience, thank you for listening. And we'll have this recording on YouTube, as always, so that you can like, comment it, and discuss it below. All right. Thanks, everyone, and hope you have a good Friday.
Thank you.
Thank you, everyone.